I want to start Unit 4, which is all about aldehydes, ketones, carboxylic acids, and the derivatives. We'll talk about why we call them carboxylic acid derivatives. I want to start off this unit by talking about what I call the anatomy of a carbonyl. And I'm not a biologist, so I may be using the word anatomy wrong. I actually don't know. But the composition, the names that we give to the different parts of the carbonyl structure. First, the reference point of our carbonyl is the carbonyl carbon. For being such an important part, the carbonyl carbon was not given its own name. So when we refer to this, we'll refer to it as the carbonyl carbon. In a similar way, we can refer to the oxygen as the carbonyl oxygen, because some of these carbonyl groups have other oxygens, like carboxylic acids and esters and acid anhydrides. They have another oxygen attached to the carbonyl, but that's not the carbonyl oxygen. Just on the example that I gave you, I gave a carbon chain to the left, but of course this isn't necessary by any means. And just a reminder that there can be anything going on here. The carbon that is adjacent to the carbonyl is called the alpha carbon. Up until this point in organic chemistry, we generally refer to the alpha carbon as the carbon of interest, the carbon with a functional group on it. Like an alcohol carbon is an alpha carbon. An alkyl halide carbon is an alpha carbon. But the carbonyl carbon is a point of interest. We're going to be doing a lot of chemistry at the carbonyl carbon, but we don't call it the alpha carbon. The carbonyl carbon has an alpha carbon. And then as the alphabet goes, the carbon past alpha is beta. In Unit 5, we're going to do a lot more about the alpha and beta positions of the carbonyl carbon. In Unit 4, we're going to focus predominantly on chemistry at the carbonyl carbon. What partial charge character can we predict around the carbonyl carbon? Oh, and sorry, just the model that you have that I gave you has put Y here on the right-hand side. Is it obvious why I would choose the letter Y to place on the carbonyl? No? What are alternatives that I could have put instead of Y? I could have put R. R is quite common. And R can really mean anything. Like I can say R equals H, R equals CH3, R equals OH. And as long as I define what I want R to be, R can be anything. But a lot of times we also subconsciously think of R as being an alkyl group, some sort of carbon chain. And it's how we abbreviate the ketone. We say the ketone has an R group on either side. So by putting an R there, I might not have been drawing your attention to all of the different types of carbonyls. What else could I have put there on the side to designate it as not just an alkyl group, but as something, a variable? X is kind of common as well, to hold a place as a variable, but in organic chemistry, X means halogen. So if I had put an X here, then I would have actually expected you to think of things like the acid chloride or the acid bromide. And those, again, are too specific. So X was too specific, R was too specific, so I chose the next common variable. That's why I've put Y. Y could be H, OH, OCH3, O-carbonyl to make an anhydride. Y could be a halide. Y could be a carbon. The Y here is just saying it's a generic carbonyl. It's not any specific type. Is that good? Okay. The chemistry that we can expect from our carbonyls. Oh, the partial charge. What partial charges can I expect to see around my carbonyl? No. Good question. I can expect to see a partial positive. Where? At the carbonyl carbon. Why? Because of the oxygen pulling electron density towards itself, away from the oxygen. So the anatomy of the carbonyl has both an electrophilic center and a nucleophilic center. The oxygen behaves as a nucleophile, and the carbon behaves as an electrophile. So, as you would expect, if you introduce the carbonyl into acidic conditions, if you give it conditions where it can be the nucleophile, there's an excess of an electrophile, then the oxygen plays a role. Introduce this into acid, and the carbonyl becomes protonated at the carbonyl oxygen. How does this change the partial charge around the carbonyl? Does it make the partial positive larger? Does it make the partial positive smaller? Or does it have no impact on the partial positive of the carbonyl? What's your intuition tell you? Doesn't change the partial charge. What do you guys think?
Maybe it's smaller.
Makes the partial positive on carbon less of a partial positive.
Well, I'm trying to think because you're adding a hydrogen on it, so the oxygen will have less like nucleophilic characteristics.
The oxygen has basically no nucleophilic character anymore. It's already acted as a nucleophile, and the oxygen won't act as a nucleophile again. So the nucleophilic character has definitely disappeared. Makes the partial positive even larger. That's your intuition, or you have something that you feel like you can justify that with?
Well, I'm saying it will make it larger because the oxygen is no longer there.
So if I remove this, then I'm essentially increasing the effect of this.
Yeah.
Maybe. I feel like we're lacking a rationale, but intuition is telling you that. That's not a bad thing. What about this? Could I use resonance to try and explain whether one is a better electrophile or not? Before my carbonyl was protonated, there was resonance. Not good resonance. Well, what is good or bad in the context of organic chemistry? Not a better contributor of resonance, but there is resonance, because resonance is the movement of pi electrons, or the delocalization of pi electrons. And here we're showing that the pi electrons of the carbonyl can move to the oxygen, which again explains why the oxygen is partial negative and why the carbon is partial positive. These partial charges exist for the same reason that this resonance form exists. But is this a good resonance form? No, because it has maximum formal charge. This is a better resonance form because it has minimum formal charge. Now let's look at the resonance form of our protonated carbonyl. Once again, electrons are taken by the more electronegative atom. And our other resonance form now doesn't look quite the same as last time. What is the difference now? No charge on the oxygen, meaning there's the same amount of charge between these two resonance forms. And charge, minimizing charge, that's rule number 1 with resonance contribution. So this breaks the most fundamental rule, try to minimize charge. This isn't really minimizing charge. Here, charge is minimized in both of them. Which of these is a better contributor to the structure? Which one contributes more? Why does the carbonyl structure on the left contribute more? Rule number 2. Or no, sorry, rule number 2. Maximize octets. Oxygen has an octet here, but carbon lacks an octet here. But there is still the same amount of charge, which means these two resonance forms contribute closer to the same amount of the molecule than these two resonance forms. I'm going to try and say this as much more of a major contributor, somewhat more of a major contributor. Meaning that positive charge on the carbon in the protonated form is more of a contributor to the structure than the positive in the non-protonated form. So resonance can help us justify what Ju was saying, which is that the partial negative is now basically gone, but the partial positive has increased. In protonated forms, we have increased electrophilicity. Oh, my niece's name is Felicity. Oh, I didn't think about that. I've got some really cute nicknames for her. Nucleophilicity. Increased electrophilicity, or if you wanted to show this another way, I like to say this as increased E+, as a way of abbreviating the electrophile. So here we have very minor contributor. And can we say this is just a minor contributor? That can help us rationalize why the carbonyl is now more electrophilic. It's still an electrophile though, which means that in the presence of a nucleophile, although this should be a good nucleophile or a strong nucleophile, in the presence of a, I'm not going to qualify that because it really depends on what carbonyl group we're dealing with. In the presence of a nucleophile, we can open the carbonyl, acyl addition. And after it's been protonated, we can also introduce a nucleophile. In this case, the nucleophile doesn't have to be as strong. a weaker nucleophile is more effective in the protonated carbonyl. A weaker nucleophile is less effective on the regular carbonyl, the unprotonated form. Yeah, I'm going to try and even put it into words. Weaker nucleophiles, like water, are more effective on protonated carbonyls. Because protonated carbonyls are more electrophilic. So something that's bad at being a nucleophile needs a lower barrier of activation to be able to react. And we lower that barrier of activation by protonating.
Are we comparing it to like the basic conditions, if you will, or like if you use a strong nucleophile, are we comparing
Yeah, so
that to that?
So think about hydroxide. We know that hydroxide is a strong nucleophile. When we were doing EAS reactions, and NAS reactions, and we wanted to substitute a halide from an aromatic ring, we needed a strong nucleophile because a weak nucleophile was not effective. Thinking of these as magnets, far too weak of a magnet to make any change in the bonds. Strong enough magnet to make a change in the bonds. Now if you think about water still being a weak nucleophile, water can't open all carbonyls. But water can open most protonated carbonyls. So by protonating a carbonyl, we improve its electrophilicity and allow for even weaker nucleophiles to attack. You want a reaction to go faster, but you're using a weak nucleophile, protonate the carbonyl. It will go faster. You're improving its electrophilicity.
So they're not more effective than strong nucleophiles, they're just more effective if you use it with a protonated carbonyl.
Good, yes. If I tried to use hydroxide, I wouldn't even be able to use hydroxide on a protonated carbonyl because it would deprotonate the carbonyl. It would remove my acidic conditions.
You want to use a weak one.
Yeah.
Kind of.
You can use a weak nucleophile even in unprotonated carbonyls sometimes. But strong nucleophiles, like hydroxide, those are effective even without protonation. You don't need the protonation for them. We'll look at the conditions. I think it will make more sense when we get into the reactions next week. But I just wanted to give you some background here. And the background is really the same. It's just saying there's an electrophilic center, and that electrophilic center becomes even more electrophilic, even more willing to accept electrons if it's protonated. But it can't be protonated in the presence of a base like hydroxide. So you'd have to use something weak like alcohol or water as a nucleophile in protonated conditions. The other thing I wanted to put on here, but I didn't put it into the diagram, is that this is not always the end of a step. Sometimes there are two different things that happen. Sometimes a reaction stops here, and we refer to it as acyl addition. Sometimes a reaction continues further to kick off some group, and we would call that acyl substitution. But they both run through or they both involve a tetrahedral carbon. That trigonal planar carbon, the carbonyl carbon, is opened into a tetrahedral carbon. And if the tetrahedral collapses back into a carbonyl, that means the tetrahedral was an intermediate. And so you'll see in some places that this is referred to as a tetrahedral intermediate. Here's what I'm worried about. I don't want you to think that acidic conditions always leads to acyl addition and nucleophilic conditions always leads to acyl substitution. Whether we do acyl addition or acyl substitution depends on the type of nucleophile and the type of reagent that we're running. Is that fair? Acidic conditions does not lead to one of these options. Basic conditions does not lead to one of these options. It's the type of carbonyl that determines which of these options happen. How can I phrase that on the diagram? Which occurs depends on reagent and carbonyl type. So we'll come back to it, but are you guys okay with just right now, we're just getting the lay of the land. We're recognizing that two different things can happen. So later in this unit, when we start looking at all of these different results, you'll see that they fall into one of two categories. Okay. Questions about the anatomy? Those of you that have had more biology than me, is that an appropriate use of the word anatomy? Do you know the etymology of anatomy? I don't either. So and maybe I'm using it right because it's components of the carbonyl. Maybe I'm not. All right, let's talk about nomenclature. What we have presented on the far left side are the different types of carbonyls. The first two, aldehyde and ketone, are distinct from all of the rest. After the ketone that you see, carboxylic acid and below, those are all considered carboxylic acid derivatives. All right, what we're going to do for each of these is talk about what suffix they get. But if you guys remember, the suffix is actually determined by the hydrocarbon part of a molecule. Alkane. Ane is the suffix for an alkane. Ene is the suffix for an alkene. Ine for an alkyne. Or ene-ine if both alkene and alkyne are present. And then we take that suffix, ane, ene, ine, enine, and we stopper the last E. We remove that last E and we stopper the suffix with something that tells us about the highest priority functional group. So far, we've only done alcohol. Alkane becomes anol. You get methane to methanol, ethane to ethanol. When we have an aldehyde, the stopper that we give is Al, al, for aldehyde. But sometimes this is not the highest priority functional group. And only one functional group can ever be the stopper of the suffix. And if a higher priority functional group plays the role of the stopper, then the aldehyde has to be described as a substituent. Like the alcohol can show up in the name as methanol, but if that's not the priority functional group, then we have to call the alcohol a hydroxy group, hydroxymethane. So the aldehyde as a substituent in the prefix is called oxo, which I think is a fun substituent name. What stopper do we give to the ketone? Own, not ket. The aldehyde starts with al. Instead of giving us hide as the suffix, but the ketone ends with own, and that's the suffix stopper that we give it. And what about if the ketone is not the highest priority functional group? What if the ketone has to be a substituent? How would we distinguish it? What would its name be? Oxo. Because the aldehyde and the ketone are both represented as a double bond to an oxygen off of the carbon chain. So there's really no distinction between whether it's an aldehyde or a ketone, but you would know whether that substituent is an aldehyde or a ketone based on where it is in the carbon chain. Is it at the end of a carbon chain? Then that oxo substituent is an aldehyde. Is it in the middle of a carbon chain? Then that oxo substituent is a ketone. All right, the carboxylic acid. You guys might know this already. The stopper is oic acid. We're not going to talk about if it needs to be a substituent because this is the highest priority group. If there is a carboxylic acid in the structure, it is named as the highest priority functional group. What about this structure? Can you say what the relationship is between this structure and the carboxylic acid? It's the conjugate base. It's a carboxylic acid deprotonated. This is called a carboxylate. Carboxylic acid becomes a carboxylate, like sulfate, nitrate, phosphate. That ate part is telling you that it's an anion. The stopper that we give to this is that we take the alkane, alkene, alkyne, and we stopper that last E with O8. There's often a counter ion. So the start of this name, it would begin with sodium something 8 or sodium something O8, like sodium benzoate, sodium acetate. We're not going to use it a lot, but I wanted to give that example of the carboxylate because when we name the ester, it is given essentially the same name. So let's say there's a prefix to this name. And that prefix would be the cation, like sodium or potassium. The ester is given the same exact stopper, O8. but now this also receives a prefix for the alkyl group. I think I wrote it as OR prime on the sheet. I didn't. Okay. Well, we don't have to then. Whatever that ester linkage is, this is how I like to refer to it. Whatever that ester linkage is, that just shows up at the front of the name. In lab, you guys nitrated methyl benzoate. The methyl was the ester linkage. So esters are named as alkyl carboxylates. Esters are named as if it's a deprotonated carboxylic acid with an alkyl group connected to it. In fact, some instruments have like a library of compounds, and they name esters as alkyl carboxylic acid ester, which is a very silly way of trying to name it. But that really does become a prefix to the entire name at the start of the entire structure. It would just have methyl, ethyl, isopropyl, phenyl, benzyl, whatever. All right, what's this next functional group? That's an anhydride. And what about the one below it? What's the difference between the two anhydrides?
Our group is different.
Yeah. We call this a symmetric anhydride because both sides of the anhydride have the same carbon chain. R is equal to R. And this we call an asymmetric anhydride. Wouldn't it be nice? No, it wouldn't be nice. Wouldn't it be funny if we tried to call it chiral? Isn't that a synonym for asymmetric? But it doesn't actually have to be chiral because sp2 carbons are planar, achiral. But it's asymmetric. If it is symmetric, the nomenclature is pretty easy. Once again, this is just given the stopper of oic acid. No, sorry, oic anhydride, which is to say it's named as if it's a derivative of the carboxylic acid. Similar to how the ester is named as if it's a derivative, you're welcome, of the carboxylic acid. And then the root that just comes in front of it is whatever shared alkyl group they have. If they have the same carbon chain, you just name it once. Benzoic anhydride, acetic anhydride, propanoic anhydride. If both sides are the same, you just name that alkyl once. For an asymmetric anhydride, the stopper is also oic anhydride, but now we name both roots. And so this makes it look a little bit more like we have two prefixes. Actually, sorry, I'm just going to phrase this as two roots. So I think this one really deserves an example to clarify it. Benzoic anhydride on the left, because both sides of the anhydride share that benzoic acid chain. And on the right, one half of the anhydride is benzoic, but the other half is acetic. So it's acetic benzoic anhydride. You get two roots, and they both get their own suffix stopper. Great. What's that next functional group? The acid chloride. And the acid chloride is given the stopper oil chloride. That is a YL. Our last two. First we have the amide, and then we have the nitrile. When I first started teaching organic chemistry, I never referred to that CN triple bond group as a nitrile. I always referred to it as a cyano group. But it shares both names. Cyano is what we call it as a substituent. Nitrile is what we call it as the primary functional group. The stopper that we give to amides is iconic. It's just amide. You literally drop the E from the root and then just finish, or drop the E from the suffix and finish the suffix as amide. This also receives a prefix. If the nitrogen is bonded to carbon groups, then we have to say that the nitrogen is bonded to carbon groups. And so we describe it as N-alkyl, N-methyl formamide, N-dimethyl formamide, which is actually one that we'll name later. It's a very commonly used organic solvent. But it's not like the anhydride where we say we just give whatever alkyl it has. It's not like the ester where we say methyl benzoate or ethyl acetate. This one we actually have to say N-alkyl. That goes right into the name. N-methyl, N-ethyl. You guys are going to make DEET next week in lab. And you're going to make N-diethyl toluamide. So there's an amide group and two ethyl groups coming off of the nitrogen. The stopper that we give to the nitrile is nitrile. And as a substituent, we refer to this as a cyano group. The one thing that we have not done is talked about priority. I'm not going to go through the priority listing for all of these functional groups because I'm not usually going to give you all of these functional groups together in a molecule. So this is a selection. Carboxylic acid sits at the top. If there's a carboxylic acid, that is assigned as carbon number 1. Always, full stop. Esters and amides are not treated the same, but I'm never going to give you both an ester and an amide in a structure. In fact, I usually don't have you name amides. I will have you name esters quite a bit, but I would have you think of those as being in similar levels to each other, especially above the aldehyde and ketone. And the aldehyde and ketone formally are recognized as equal priority. And you know the trouble that comes from having two equal priority functional groups. If they're both in the structure, which one do you prioritize? The alkene and the alkyne are of equal priority. And what we've said with alkene and alkynes is that if one of them can get the lowest possible locant, then give that lowest possible locant to whichever one. If both functional groups in the compound get the same lowest locant, then the tie goes to the first alphabetical. But in this case, the debate between aldehyde and ketone, one of these functional groups will always get the lowest locant possible. The other can never get the lowest locant possible. Is it obvious which one? Always gets the lowest locant. Why? The aldehyde has to be at the end of the carbon chain. So the aldehyde will always be at carbon 1, and the ketone can't be at the end of the carbon chain. So aldehyde takes priority over ketone if both are in the structure. And remember, I can't have more than one suffix stopper. I can't name my compound butanone-al or butanal-one. I can only have butanal or I can have butanone. So the other substituent or the other group is named as a substituent. It's given the term oxo in the prefix. After these, I'm not going to have you focus on where the priority of the carboxylic acid anhydride is or the acid halide. After these, I want to remind you that the alcohol has high priority, and then alkene and alkyne are tied, and then regular alkyl groups, methyl, ethyl, tert, butyl, and halogens, bromo, chloro, iodo, tied for the same priority, just like we saw in OCHEM 1. Brenna, you're pretty well caught up on this side, or you need a little more time? Okay. Can you tell me what this cluster of 6 compounds on the right, the top right, can you tell me what that cluster of carbonyl compounds have in common? Sorry? They only have carbonyl carbons. That's true. Although the ester has an R group, and we don't really know what's going on at that R group, but we know that R group can't be a carbonyl, because if this R is a carbonyl, then it's actually an acid anhydride. So they all have a carbonyl carbon, but that was true of all of this as well. The ester kind of throws a wrench into it. Can we add more to that? They all have a carbonyl attached to a hydrogen, which means that they all would be classified as aldehydes. The aldehyde is a carbonyl bonded to a hydrogen, right? What I would say, or the way that I frame this, is that these are one carbon carbonyls, or essentially derivatives of an aldehyde. Okay, so the simplest one. CH2O. You guys know this compound. We've talked about it in the alcohol chapter. And I know you've heard of it. The name? Formaldehyde. Okay, but that doesn't use the rule that we just established. The rule we just established was that you assign the parent chain as normal, you give a suffix based on the highest priority hydrocarbon, and then you stopper that suffix with al to indicate aldehyde, and this has no root, no suffix stopper. This is a common name, formaldehyde. The form indicates the one carbon carbonyl. Aldehyde tells you that the other side of it is the aldehyde. A systematic name for this compound, a IUPAC name rather than a common name, one carbon, meth, no alkene, no alkyne. So the suffix is ane, but it's not methane, that's CH4. So we stopper the E with Al. This is methanal. Makes sense, right? A one carbon aldehyde, methanal. But you will hear it referred to as formaldehyde. Okay, the one just below it. Maybe a compound that you guys have not heard the name of before, but also maybe you have. It's a one carbon carbonyl, so its root in terms of its common name is form. This is formic acid. You guys heard of formic acid? Formic acid is a Greek, it comes from Greek origins. The Greeks noticed that when they crushed up ants, they could extract this acid from them. And so they described this as the acid that comes from ants. Form is Greek for ant. Not ant like paternal or maternal ant, but like the largest biomass of any creature on Earth, ant. Do you know that? Ants make up more biomass on Earth than any other creature. There's a larger biomass of ants than any other animal's biomass. Even humans. Yeah, it's pretty crazy. Okay, anyways, formic acid. What would be a systematic name? Methanoic acid. Now I want to point out a difference between this systematic name and the common name, and it's the O. The systematic name, I told you that it should go oic acid, but we don't call it formoic acid, we call it formic. So for whatever reason, in common names, that O is often dropped. Acetic acid, vinegar, it's not called acetoic acid. Formic acid, rather than formoic acid. In common nomenclature, in systematic nomenclature, that O is there. In common nomenclature, you won't see it. All right, the one below it. Now, I recognize that we don't know what the R group is, so I'm going to show you guys how we can name that generically. In terms of its common name, since we don't know what R is, we can just say alkyl, but that would be methyl, ethyl, phenyl, benzyl, alkyl formate. Methyl formate is a compound we'll work with in later in this chapter, or later in the semester. But the systematic name for it would be alkyl methanoate. Look at that, the O dropped again. Methanoate versus formate instead of formoate. I really think that this is just because of how it rolls off the tongue. I don't think that they have any other rationale besides that. Can you give me both the common and the systematic name for this compound? Someone give me the common name. No. Formic anhydride. Remember, in that common name, the O is not assigned. And the systematic name for this compound? No. We don't have to add any multiplier. If it's symmetric, we just name it once. So methanoic. Remember, the O comes back. Not dimethyl anhydride, but methanoic anhydride. Can you give me the two versions of this compound's name? Remember, the O is going to drop, which gives us formal chloride. Wow, chloride, you're dressed so formal today. Get it? And the systematic name? Methanoyl chloride. All right, last one. Keep in mind that this amide has no R groups coming off of the nitrogen. So there will be no prefix of N-alkyl. There is no alkyl group off of N. So what systematic name do we give it? Sorry, common name.
Formide. You dropped the A this time?
Not formide, right. We don't drop the A. Formamide. I know. I didn't make the rules. I wasn't invited. And the systematic name, methanamide. The thing is, I will only require you to know the systematic nomenclature. But you are never going to see these compounds named with the systematic name. You're only ever going to see them by their common names. People aren't out there telling you to go run a reaction with methanoic acid. I wish they did. Can you tell me what the second set of 7 compounds have in common? And if you're struggling, I don't blame you. There's a part of this that I really don't like. Oh, I forgot one as well, actually. That CH3CN. I wanted that one on there. Oh, so close. Yeah. The nitrile is thought of as similar to a carbonyl, but it's not a carbonyl. It's a relative of the carbonyl. So they all have an alpha carbon. If you think of this as the carbonyl carbon, the nitrile carbon, they all have an alpha carbon. I think that's a good way of looking at it. I phrase this as 2-carbon carbonyls. But one of these is actually an outlier on that. One of these is not a 2-carbon carbonyl, it's a 3-carbon carbonyl. So in order to convince you that it really is a 2-carbon carbonyl, I'm going to show you a perspective. The first one at the top is called acetaldehyde. And that acid part tells us 2-carbon. The systematic name for a CH3CHO two carbons, F, only alkane functionality, or rather, no alkene, no alkyne functionality. So ethanal. I'm going to skip the next one. This is a compound you're all familiar with. This is acetic acid. Notice the ACET part, acet, telling us that we have a 2-carbon carbonyl, but it could be called ethanoic acid. Down below we have an alkyl acetate. Once again, acet, telling us that we have a 2-carbon carbonyl structure, or alkyl ethanoate, like methyl acetate, ethyl acetate, methyl ethanoate, ethyl ethanoate. Okay, I'm running out of time. I think we'll maybe have to pick up here tomorrow. Well, I'll finish off the rest of these tomorrow, but I'll give you guys what they are, and we can. Why am I saying tomorrow? Like we're going to come in tomorrow. Next week we'll pick up with finishing this nomenclature. Acid chloride. Acetic anhydride, acetyl chloride, acetamide. You guys ever heard of a compound that includes the name acetamide? acetaminophen. Acetaminophen has a 2-carbon carbonyl amide. You hear it now, right? Acetaminophen. Did I say its name wrong that whole time? Okay. Acetaminophen has that 2-carbon carbonyl amide. Acetonitrile is a very common solvent for some instrumentations. Acetamide, acetyl chloride, acetic anhydride. What would we name this? So it's a 2-carbon carbonyl ketone, which means it's a 2-carbon carbonyl if you look at it from this side, and it's a 2-carbon carbonyl if you look at it from this side. So it's a 2-carbon carbonyl aldehyde? No. A 2-carbon carbonyl acid? No. A 2-carbon carbonyl amide? No. It's a 2-carbon carbonyl ketone from whichever direction you come from. So they call it acetone. I hate it here. That is the dumbest example of common nomenclature making no sense. But you've known about acetone forever. You've never once questioned its name, have you? Why do they call it acetone? Because it's a 2-carbon carbonyl ketone in both directions. The more you know. Thank you guys for your time. I'll see you on Tuesday, where we'll do some practice with nomenclature, and then we're going to get right into reactions with aldehydes and ketones. Enjoy your weekend.